Hello students, welcome to 8th lecture of surface chemistry. In previous lecture we were discussing about catalyst. So let us proceed further. Today we are going to talk about characteristics of enzyme catalyst. So enzyme catalyst, as discussed earlier, it is natural catalyst, and in plants and in animal bodies, even in our bodies, we have different type of enzyme catalyst. So enzyme catalyst is unique in its effectiveness and high degree of specificity. Now, as it says high degree of specificity, that means if a reaction inside the body or inside the plant uses, let us say, catalyst A, then same catalyst will be completely useless for other reaction. As for example, suppose if you want to decompose glucose inside the body to produce energy, then you have to use specific required enzyme for that reaction only, and same catalyst will be completely useless for other reactions. The following characteristics are exhibited by the enzyme catalyst. First is most highly efficient. One molecule of enzyme may transform 1 million molecules of reactant per minute. That means they are highly efficient. Second, highly specific nature. Each enzyme is specific for given reaction. That is, one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. So as we can see, urea is a one type of amide compound, and it undergoes hydrolysis process in the presence of urease catalyst. Now if you have same type of functional group in other molecule and same type of reaction, that means as we can see here, we have hydrolysis reaction, still urease enzyme will be useless for other amide molecules. Next, highly active under optimum temperature. The rate of enzyme catalysis becomes maximum at definite temperature, called the optimum temperature. On the other side, the optimum temperature, the enzyme activity decreases. That means if you increase or decrease the temperature, then effectiveness of the enzyme decreases. That's why our body maintains specific temperature. In case of fever, if temperature increases, then it will disturb the enzymatic reactions inside the body, and that's why overall system of body will be disturbed during the fever. The optimum temperature for this type of enzymatic reactivities is 298 to 310 Kelvin, and our body temperature is almost near to 310 Kelvin. That's why it is suitable for enzymatic reaction. Highly active under optimum pH. Again same point, we have to maintain conditions for enzymatic reaction. Our body again maintains the certain level of pH. If it get disturbed, then it will disturb the enzymatic processes. The rate of enzyme catalyzed reaction is maximum at particular pH, called optimum pH, which is between 5 to 7. Increase in activity in presence of activators and coenzymes. So as discussed earlier, in case of catalyst, if we use promoters, then it will increase the catalytical properties, and if we use poisons, then it will decrease the catalytic properties. So same type of behavior coenzyme shows. So activators and coenzymes are again some molecules which activates enzymatic processes and helps in enzymatic processes. So enzymatic activity is increased in presence of certain substance known as coenzyme. That means it will behave as promoters. It has been observed that a small known protein called vitamin is present along with the enzyme. The catalytic activity is enhanced considerably. Okay, so that's why very small quantity of vitamins are important for us, because they will increase the catalytical activities of our enzymes. And activators are metal ions like Na plus, Mn2 plus, CO2 plus, Cu2 plus, etc. These metal ions, when weakly bonded to enzyme molecules, increases their catalytic activity. Amylase in presence of sodium chloride, that is Na plus ions, are catalytically very active. And influence of inhibitors and poisons, last point. So, like ordinary catalysts, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitor or poisons interact with the active functional groups on the enzyme surface and often reduce to or completely destroy the catalytical activities of enzyme. The use of many drugs is related to this action as enzyme inhibitors in the body. You will learn about this point in detail in this unit as well as in unit 14 biomolecules. So now let's talk about the mechanism of enzyme catalysis. So enzyme catalysis contains number of cavities present on the surface of colloidal particles of the enzyme. Now what is colloidal particles? So we discussed it earlier, but let us quickly discuss it again. So when we dissolve molecules like sodium chloride inside the water, they will dissociate and very small tiny particles of these solutes will be mixed with the water, and these type of particles are so small that they do not disturb incoming waves of visible light. That means let us assume this is the size of solute particle and this is the wavelength of our visible light. So as we can see, wavelengths are bigger than our particle. So no interaction between particle and wavelengths will be observed. But if we increase the size of this particle, then situation will be different. Now if particles are larger in size than the wavelength of our visible light, then these lights or waves must have to interact with this particle, and because of interaction between this particle and wavelength or wave of light, they will either change their direction or maybe they will bounce back, that means reflect. So because of these type of properties observed with the larger sized particles, if we dissolve sufficient large size of the particle inside the solvents, then they will produce blurry solutions, and it is called colloidal solutions, and those larger size particles are called colloids. Okay, so that means it is just like solution, but it has comparatively larger particles of solutes. And here we have example of this type of effect. So as we can see, we have two different beakers. Let us call it beaker A and beaker B. So in beaker A, no light is being observed, while in beaker B we can see the path of light. So why these type of effects are observed? In first beaker we have solution, that means we have very small particles which are mixed with the water. In second case we have slightly larger sized particle dissolved inside the water. So that's why in beaker A no interaction occurs between the particles of solute and light. On the other hand, with the beaker B we have larger sized particle, that's why these particles will interact with light and they will scatter the light. That means if light is coming through this direction and when they collide, these light rays collides with the colloidal particles, they will randomly change their direction. That's why we can see the illuminated path of a beam of light from all the direction when it is coming out of colloidal solution. On the other hand, when this light beam passes through the solution, no interaction between the solute particles and light beam is being observed. That's why light beam will pass through it without any scattering, and that's why you cannot see the beam of light. If you want to observe the beam of light, then you have to see it from this side. So in short, colloidal particles are larger in size than our regular solute particles. And a simple example, you can observe it yourself: gum or milk. These are the common example of colloidal solutions. So these cavities are of a characteristic shapes and possess active groups such as NH2, COOH, SHOH, etc. These are actually the active centers on the surface of enzyme particles. The molecule of the reactant or substrate, which have complementary shape, fit into these cavities just like a key fits into a lock. So here this demonstration is made by lock and key mechanism. So let us say we have a specific enzyme, as we can see here, shaped like a key, and the shape of this enzyme is complementary with the shape of substrate. That means that's why we can say that this enzyme only works on this substrate, because their shapes matches with each other, or they are complementary of each other. So initially we have enzyme and our substrate, so they will combine with each other and they will form a complex enzyme substrate complex called ES. Then enzyme will be separated out from the substrate and substrate will convert itself in product molecule. So that means to obtain product from the substrate, enzyme helps. And from this demonstration we can say that why enzymes are highly specific. That means you cannot use one enzyme for other reaction. Just like keys, one single key works with one lock only. You cannot use same type of key for other lock. So this enzyme catalyst reaction occurs in two steps. First step is binding of enzyme to the substrate to form active complex. So E plus S gives ES star, and second, decomposition of this activated compound or complex. That means ES gives E, that means enzyme, plus product. So next is a catalyst in industry. Few important examples are mentioned here. So first is Haber process for the manufacturing of ammonia. So simple process is N2 when reacts with H2 gives NH3. But this is not a very simple reaction as it seems, and you can observe it from the list of catalysts mentioned here. So finely divided iron molybdenum as promoters, conditions 200 bar pressure and 723 to 773 Kelvin temperature. Nowadays mixture of iron oxide, potassium oxide and aluminium is being used. Second is Oswald's process for manufacturing of nitric acid. First, NH3 reacts with oxygen and gives NO gas. NO reacts with again oxygen and gives NO2. NO2 reacts with water, oxygen and finally gives HNO3. And as a catalyst, platinized asbestos and temperature requirement is 573. And last is contact process for manufacturing of sulfuric acid. So SO2 reacts with oxygen and gives SO3. SO3 with H2SO4 gives H2S2O7. And H2S2O7 OLEM when reacts with one more water molecule it gives H2SO4. That means sulfur trioxide reacts with one molecule of sulfuric acid and produces OLEM. When OLEM reacts with one molecule of water, it produces two molecules of sulfuric acid. That means in this step we are using H2SO4. How many moles we are using? 1 mole. And in last step you are getting 2 moles out of it. That means if question in your mind arises why sulfuric acid is being used instead of being produced, okay, so this is the reason. If you use 1 mole then eventually you will get 2 moles of it. That's why we are using it as a reactant, which is our main product. So platinized asbestos or vanadium pentoxide temperature requirement 673 to 723. From next lecture we will discuss about colloidal solutions or colloids.